All right, everybody. It's another good day in the physics classroom here. We're looking at, a little lonely though, we're looking at addition and subtraction of vectors with components. And so we're going to put together the idea of how to add and subtract vectors, and then the component work from lesson 28. We're now putting it together to be able to actually add and subtract vectors using components. So getting answers mathematically instead of having to trust and draw really careful scale diagrams. Okay, so as part of this, it's important for you to recognize that you really should still sketch the diagram. You just don't need to measure anymore. So it's not a scale diagram. It's just a good representation of the concepts. Okay. So with adding three vectors, tip to tail, for example, you'd show the three vectors, whatever they were, something like that or whatever. And, your result is here and so on, right? And you'd be able to use this diagram to help you through the work for combining the components. And so basically you'd have a component here and a component there. So an x1, y1, let's call it, for vector number 1, and then an x2 and a y2 for vector number 2, and an x3. So an x. So vector 3, sorry, I just messed myself up by putting x3 there, that's all. So vector 3 would have an x and a y, right? So an x3 and a y3. And we'll get to the end where we're able to use that to get the final answer, and I might come back to that one and just round that up, or finish that up at the end. All right. So to start out with, let's just look at a question like this. If you started at a position of, so that's the word for that one from the previous lesson, right? Position of 6 meters east, 20 degrees north. It just locates you in space on the map, basically. And you ended up at a final position, so of 9 meters north, 30 degrees west. I want you to determine the displacement. And so we're going to do this with math this time instead of with scale diagrams. So I have a bunch of slides lined up ready to go for this, where the first thing is to recognize what kind of process you're doing. Are we adding or subtracting? Well, displacement, right? Pause and think about it if you want, but displacement is final minus initial, always, right? Any change is always final minus initial. So we're looking at d2 take away d1, essentially, final minus initial. And so it would be useful to do tail-to-tail vector subtraction. Resist the incorrect assumption that 9 take away 6 would be 3. It's not going to be 3. Angles matter. Okay? So if we sketch the diagram, we'll be able to use it as a guide for combining the components. Okay? And we're going to show those x and y components on the graph, on the drawing, like I did here. And then eventually you're going to trace out the path along the known components from start to finish. And so if I went back to this one, think about if I was going from start to finish, from here, from initial to final here for this overall displacement, right? You'd actually kind of trace out the path. You'd be like, okay, I'm going to go through that x displacement, and then I'm going to go through that y, and then I'm going to go through this. These are known values now because you can calculate each of those components. And so quite literally, we keep track of all of them. And there was an x1 component, and there was an x2 component, and there was an x3 component. We're just combining them all, right? And so it's I'll show at some point in this lesson as well the idea that you're going to establish an x and y reference frame. So based on that, all three of those were to the right, so they'd all be positives. And then the y1, the y1, the y2, and the y3 have some different signs to deal with, because the first one was up, the second one was also up, and then the third one was down, right? And so you'd get a grand total just by adding these up, right? By adding those all up, you get totals and so on. So we've seen something like that already. The only thing new is that we get those values in a previous lesson, right? Like lesson 27 or something, we saw that. The only thing new now is we're going to get the values from math work to do with components. Okay, so this orange path from start to finish is an important concept. So I'm just trying to get you to understand what I mean by that. And then I showed you there the idea of choosing your positive and your negative directions, basically. Should say x and y there even, but whatever. So if we draw the vectors, right, we got this 9 at 30 degrees north 30 degrees west. So this represents the D2, the final position. D1, 6, I just have them placed when I moved them onto this page. I just moved them so that they fit into this space. But yeah, D1 is 6 meters, what is it? East 20 degrees north, right? East 20 degrees north. I was just looking here, east, and then 20 degrees north. Yeah, so those are your vectors. And then so to represent this vector subtraction, we would need to put them tail to tail. So that's this slide, right? You can see them actually tail to tail here. So once they're tail to tail, then you can go ahead and actually do a bunch of calculations. You can calculate the x component and the y component, the x component and the y component, get all those values. And so that's all worked out here, basically, where you can look and say, okay, well, if I want the x component, I'm adjacent to the 20. So I'm going to do the 6 times cos 20. The signs I'll deal with in a minute, okay? But right now it's just 6 cos 20, and then this is opposite the 20, so 6 sine 20, and this is adjacent to the 60, right? So if we're using 60, the complementary angle here, you'd have cos, or you could have thought of the x component being up here, in which case it's opposite the 30. I'll probably encourage you to just get the angles that fit nicely in the diagram. So if you use the 30, you'd have to have your x component up here and your y component here. And so your path from one to the other would be a little different, but that would still work, right? So this x component would be your 9. And then we're talking about opposite the 30, so sine of 30. So based on yesterday's lesson, it's super easy to look and see, like, are we opposite or adjacent? If we're opposite, use sine. If we're adjacent, use cos, right? Rather than having to start with sine or cos and solve for the missing piece every time. It works out to just the size times sine or cos of the angle. So the sines, I said I'd talk about in a minute here. We need to look at the fact that this is our initial right here. That's our initial position and our final position, or our final value. So it's final minus initial, right? So basically you can tell, like, this is our displacement and the direction is that way, right? So when I talked here about trace out that path, it looks like this, where you go down this way and then you go back this way and then you go back some more and then you go up finally. So all of these are negatives, negative, negative, and negative, based on the usual direction system of the x and y being to the right and up, being the positive directions. Okay, so all of those values just are what they are. And so the two negative x components show that you went fairly far to the left, right? You went to the left and then you went to the left some more and so on. So the signs just have to be logical relative to each other, really. Yeah. So the next part here is trace out that path. So it looks like that all the way along. And then all these numbers that we have from doing components, that's just yesterday's lesson put to use, right? You just make a table of values and combine them all. So this nice organized table of values is something that a friend of mine, Greg Davidson, in university, showed me, because I was all over the map. I wasn't organized, and it was hard for me to keep track of what numbers needed to be added, and I kept making mistakes. He's like, oh man, just put it in a nice table, have all your x's and all your y's, and just combine them and get your total x and y, right? So you have a total. Remember, I said it's going to be fairly far to the left because we went to left and then to left some more. We went down, but then we went up more. So as a result, we went up overall by a smaller number, of course. And then, yeah, you just have to add them all up, get your resulting components in each direction. And then you can show that on your diagram even if you wanted, right? This up of 5.75 and to the left of 10.3. The bracket around the negative is basically because when you're doing geometry about the triangle, you don't worry about the negatives. But in the context of, like, I went, left instead of right, or whatever, backwards instead of forwards, the negative is meaningful. So you have to kind of be careful about the negatives when you're doing the triangle work. So that triangle, this triangle right here, good to just redraw that when you go to do your work. And so the length is always just the Pythagorean theorem, and physicists always just pretty much just jump right to this line here. right? You just do the root of both sides and say, okay, the displacement is the root of the sum of the squares from the Pythagorean theorem. So you get that number for the total displacement. And then for the angle, you just look at the triangle and use the angle from the starting point, whichever one's natural fitting here, right? So this one ends up being a vertical angle to the vertical. So tan of that equals opposite over adjacent. So opposite over adjacent, you do tan inverse, you get your number, and you're done. So that's the displacement, right? So that's, you know, a number that you'd get close to if you did a nice scale diagram. I forget whether we did this exact one or not. If we did, go back and look in the lesson and you'll see like, oh yeah, there we go. We got 12 last time we did the diagram and by scale and so on. And then, you know, the actual number is 11.65, for example, right? So that's the process. What I went through there, that's the process you want to be able to do depending on whether, you know, the only thing that changes is what kind of setup you had for your vectors, right? So here we did a tail to tail because we're doing vector subtraction. The very start, I looked at like tip to tail along the way, and you know, you add up and get your total number. So tip to tail giving you addition, tail to tail, and the one we did in detail giving you subtraction. So I do want to point out that this example that I went through thoroughly here could be done with sine and cosine law, right? You have this triangle and you'd be like, okay, I can figure out this angle is 100. That might be a stumbling point. And then recognize, be like, okay, choose which you're going to use, sine law or cosine law. The way I teach sine law in math classes, if you have a crisscross of information, you can use sine law. If you don't, you just use cosine law. It's kind of a little bit more straightforward way of picking which one you can use. So in this case, you don't have a crisscross of information, meaning like an angle and an opposite side where you know the values, and then another angle and another opposite side where you're like missing one of them, right? So basically in a crisscross, if you have all angle side and angle side where you're just missing one, you can use sine law. If you don't have that, then you resort to hoping to be able to use cosine law. For cosine law, of course, you know, you're given that angle, so you're certainly going to use it. And then that opposite side is your displacement, and yada yada. You can get the value, and then you work towards getting the angle, and it's just more complicated, right? It's higher level math skills, I guess, needed for it. So what I'm saying there is using sine and cos to get components and combining them is just easier. There's no higher level stuff needed. Plus, in the question that I started out with, where 3 all added up, that's not just a triangle. So you can't just use sine or cosine law anyways. So we need this process of components. And so really I'm saying here for this class, I'm not really requiring you to do this at all. I wanted to show it to you. First reason, because it's a bit more mathy than I want grade 11 physics to be. I like to focus on physics concepts way more. And you need the component method anyways, in cases where you have more than one vector. So it just makes sense to go with the process that works, right? So if you're looking for another example, this is one here. You know, if you're given V1 and V2, there's a number. This is one of those numbers. I forget which one, but you know, you started at a velocity of this, and you end up with velocity of that. When you're getting your change in your velocity, it's just V2 minus V1. So it's the same kind of work. So place them tail to tail, trace out the path, and so on. Okay. That's about it. I had a page here about, you know, that number 3. If you wanted it to be components, you'd have to have angles, right? So I just scratched it off for my own note purposes to say like, okay, let's not waste our time doing that one this time. But you know, if you had angles, you could do it by components rather than just drawing scale diagrams or measuring right from the scale diagram, that is. So that's it for that. Now I'm going to give more time for this one because you have the previous version of this where you're doing scale diagrams, and I want you to have an opportunity to do several. Do a scale diagram of this and then see what you get from the math, right? A lot of these are the same questions as lesson 27, I guess it would be. And so you have a chance to see what you get by a scale diagram and then do the math version of things, and you can compare it, and then you can compare them, right? So I need you to be able to do both methods on an assessment, the scale diagram and the component method mathematical process. All right, so that's it for me for now. And yeah, until next time, take care.